Valeem, learn this smart way. So we are going to talk about A-Levels Chemistry 9701. I'm the instructor, Mrs. Ghazala Arif, MS Chemistry, and I have 13 years of experience in Pakistan and as well as abroad on international level for teaching CAIE A-Levels and O-Levels Chemistry. And today our topic is ionization energies from atomic structure. The learning outcomes, what we need to know today is state and explain qualitatively the variations in atomic radius and ionic radius across a period and down a group. Define and use the term first ionization energy. Construct equations to represent first, second, and subsequent ionization energies, that is successive ionization energies. Identify and explain the trends in ionization energies across a period and down a group in the periodic table. Identify and explain the variation in successive ionization energies of an element. Understand that ionization energies are due to the attraction between the nucleus and the outer electron. Explain the factors influencing the ionization energies of elements in terms of nuclear charge, atomic radii, ionic radii, shielding by inner shells and subshells, and spin pair repulsion. Now here we go with the electronic structure and atomic radii. As we can see, what is the trend of atomic radius throughout the period, throughout the period and down the group. So we need to see that as we move across the period, what happens? The number of shells remains same, but the electronic charge and the nuclear charge increase. Okay, so the what happens, the ionic attractions, the electrostatic attractions between the nuclear and the valence electrons, they are going to increase throughout the period. So this will result in decrease in atomic size. But when we look at the down the group, what happens? The shells are added down the group. Okay, so the distance of the outermost electrons from the nucleus will increase, and this will decrease the nuclear effect on the valence electron, and it is easy to eject the electron out of the atom. So this results in decrease in ionization energies down the group. Now let's have a look at the ionization energy. What does it mean? The first ionization energy of an element is the energy needed to remove one electron from each atom in 1 mole of atoms of the element in the gaseous state to form 1 mole of gaseous ions. So this is the definition of ionization energy, and it is represented by the sign symbol delta Hi, enthalpy of ionization. The symbol for the first ionization energy is delta Hi1. Using the calcium as an example, calcium is an element with atomic number 20 and it belongs to group 2. That means it has 2 valence electrons in its outermost shell. First ionization energy. Calcium will lose 1 electron in its gaseous state and it will form unipositive ion. The enthalpy, first enthalpy of ionization to eject this electron is 590 kilojoules per mole. Now let's have a look. If a second electron is removed from each ion in a mole of gaseous ions, we call it the second ionization energy, delta Hi2. Again, using calcium as an example, the second ionization energy equation is, now this equation is written from the calcium ion, not from the atom. In its gaseous state, we are going to eject another electron and we are going to form dipositive ion, calcium Ca2 plus. And second enthalpy of ionization is 1150 kilojoules per mole, which is almost double of 590. Now let's have a look at removal of a third electron from each ion in a mole of gaseous 2 positive ions is called the third ionization energy. Again, using calcium as an example, the third ionization energy, that means removing an electron from dipositive ion, will require now 4,940 kilojoules per mole of energy. This is a huge jump. And what does this successive ionization energy is telling us? That there is the electron we are going to eject now is now from the next shell, inner shell. And inner shell is complete. It is already following the electronic configuration of noble gas. So we need to have high energy to eject that electron from the inner shell. So this big jump always tell us that we are moving to the inner shells. Now, which are near to nucleus. Now, these are the successive ionization energies of period 3 elements. Let's have a look at sodium. We have 496. The first ionization energy for sodium is 496 kilojoules per mole. For magnesium, it is rising 738 kilojoules per mole as atomic radius is decreasing along the period. So ionization energies tend to increase along the period. But in case of aluminium, we will see that there is a change, 578. Instead of increasing, this ionization energy is decreasing. Why this is happening? Because aluminium is having the third electron in the p orbital, and that is a higher, this orbital is a little higher. Okay, magnesium is having the two electrons in the s orbitals and it is having a stable configuration, so we need to uh, put more energy to eject those electrons. Whereas in aluminium, one electron is now residing in the p orbital, and it is easy to eject that electron because it is a little it is at a little higher energy state. Now let's look at the sulfur. Sorry, let's have a look at the silicon. This is 786 kilojoules per mole of energy. Again, the energy is increasing. Then we have phosphorus, again 1012 kilojoules per mole of energy. But we will look in case of sulfur. What is the trend again? We have 1000. Instead of rising, this energy is decreasing. The reason is again that in sulfur, in p shells, the electrons start to pair up. Okay, now we have two paired electrons in the px orbital, and it is easy to eject that electron because when two electrons are paired up in one orbital, they are going to repel each other. So this repulsive force between the electrons making it easy for us to eject the electron. So that's why this enthalpy of ionization, first enthalpy of ionization for sulfur is decreased. Then for chlorine, it's increasing, and for argon with very stable configuration, it is very high throughout the period. Now, another thing which we can get from the another idea which we can get from the successive ionization energies is, as there is a huge jump, that means this tells us to help with the electronic configuration of the elements. Sodium belongs to group 1, so it has one electron. The second electron is from next shell. Now, magnesium belongs to group 2, so two electrons are having successive ionization energies with a regular increase, but then a huge increase is there. That means inner shell is started. Aluminium is having 3 electrons in its valence shell. Then a huge jump is telling that the next electron is present in the next electronic shell. Silicon is having 4 electrons in its valence shell. The huge jump is telling that the next electron is in the next shell. So on. Okay, and next, now let's have a look at the factors that influence ionization energies. Number 1, the size of the nuclear charge. Number 2, the distance of outer electrons from the nucleus. Number 3, shielding effect of inner electrons. Let's have a look at them in detail. The size of the nuclear charge increases down the group, and so does the number of shells. So what happens? The effective nuclear charge decreases, whereas in the period the nuclear charge increases, as well as the number of electrons increase also. Okay, so what happens to the atomic size? The atomic size decreases along the period, and the atomic size increases along the group. Now let's have a look at distance of outer electron from the nucleus. Okay, this is also called atomic radius. We cannot take the atomic radius of an atom because it's a very small unit. So what we take, atomic radius, is half the distance between the nuclei of two bonded atoms. That is measured and then it is halved. When we look at the lithium in group 1, lithium is the second element with having 3 electrons and 1 electron in the valence shell. This is the distance of the nucleus and the valence electron. But when we look at the potassium, potassium belongs to group 4. So when we look at the potassium, we can see that the valence electron is farther away from the nucleus. So this decreases the ionization energy. That means it is easy to eject this electron from the valence shell as compared to eject this electron, which is under the more hold of the nucleus. So what we have learned from this slide, that nucleus charge decreases, the nuclear force decreases with the increase in number of shells. Now, let's have a look at electron shielding. What happens when we are talking about the bigger atoms, which are bigger in size? The inner electrons, which are present in inner shells, the core electrons, they are going to shield the valence electrons from the nuclear attraction. So, electron shielding occurs when the inner shielding electrons shield the outer valence electrons from the full attraction of the nucleus. The valence electrons within an atom require less energy to remove than the inner electrons. Now, let's have a look at sodium. We can see that the configuration of sodium is ending at 3s1, and it is easy for us to eject this electron. The trend of the ionization energy down the along the group is that the ionization energy tends to increase. But over here we are observing that for magnesium it is increasing, but for aluminium it is decreasing. What is the reason? The reason is that magnesium is having stable electronic configuration, so it is difficult for us to remove this electron from this stable configuration. Whereas in case of aluminium, we have this unpaired electron present in the p orbital, and it is easy for us to remove this unpaired electron. Now, let's have a look at the silicon. Again, there is a trend, increasing trend in the ionization energy. For phosphorus, uh, it's increasing. But in case of sulfur, again, there is a decrease. The reason is now this p x electron is paired up with another electron, and there is a repulsion between the two, so it is easy for us to remove the valence, this valence electron of the sulfur. For chlorine, it will increase. For argon, which is a noble gas, it will increase because it's stable. So it's difficult for us to remove the valence electron. Now let's have a look at the ionization energy graph. This is hydrogen. It's very easy to remove the valence electron of hydrogen by applying the energy. Now let's have a look at helium. Noble gases are always at the top of the graph. Now let's have a look at this lithium. Lithium's ionization energy is lower, and then throughout the period it will rise, except for group 3 and group 6, because of the unpaired electron for group 3 elements in p orbitals, and for group 6 because of the pairing up of the electrons in the p orbitals. It's easy for us to remove the electrons. Now the overall trend is that group 1 elements are always present at the bottom, and group 3 elements are always showing a decline. Similarly, group 6 elements are showing a decline. The net trend is increase in ionization energy for whole of the period. So these are the points which we need to remember when we are analyzing the data of the ionization energies. Now this is how the electrons are paired up in an orbital, and this is how they reside with opposite spins. The minus half is telling us a spin in clockwise direction, whereas positive half is telling us a spin with anti-clockwise direction. In hydrogen we have one electron. In helium we have two electrons in the s orbital. This is the stable configuration. In lithium we have one electron in the s orbital, and it is easy for us to remove this single electron in the valence shell. For sodium, again, you can see in s orbital, 3s orbital, we have one electron, and it is further away from the nucleus. So it's very easy for us to remove this electron. So the ionization energy of sodium will be much less as compared to lithium. Let's have a look at oxygen. For oxygen, we have this paired up electron, two electrons in px orbital, and it is easy for us to remove this electron, this paired up electron, because of the repulsion between these two. Okay, and then chromium is a transition element. We are not going to discuss it over here. Then let's have a look at the electronic configuration of four atoms as shown. Which atom has the highest first ionization energy? 3s2. Which element is that? The 3s2 element belongs to group 2. So it is supposed to be magnesium. Then 2p4. Which element is this? The electronic configuration with 2p4. Let's have a look at the slide behind. 2p4. It's oxygen. So it's easy for us to remove the electron from oxygen, right? Now 2p6, that means this is a complete configuration. This is a noble gas. Okay, so it's very difficult to remove the electron from a noble gas again because of the stability. Then 1s2 2s2, this also belongs to uh, 1s2 2s2, this belongs to group 2 element, and this is going to be which element? uh, Beryllium. This is beryllium. Okay, so due to stability, it's also difficult for us to remove the electron from this shell. So from out of these four options, option C is totally ruled out. Okay, and when we look at the B and D, it's easy for us to remove the electron from the B because of the unpaired electron. But when we look at the 3s2 electron, let's have a look over here. 3s2, this is 3s1. So okay, so magnesium is 3s2. So it's easy for us to remove the 3s2 electron. Now let's go back at the graph. Look over here, this is 3s2. Okay, and we can see that all the p electrons are at a high energy state as compared to this 3s2 electron. So by having the idea from the graph, by learning these ionization energy graph, we can solve our questions. So our option is A. Now let's have a look at the next MCQ. The first ionization energy of beryllium is higher than the first ionization energy of boron. Beryllium is having atomic number 4 and boron is having atomic number 5. Which statement explains why? Boron has a full outer shell? No. So this option is ruled out because it has 3 electrons in its valence shell. Boron has a larger atomic radius than beryllium. Not possible again because the atomic radii tend to decrease across the period and boron comes after beryllium. Then beryllium has a more stable electronic configuration. Yes, we can look for this because beryllium is having 2 electrons in its s orbital, whereas boron is having its 1 electron in the p shell, and it's easy for us to extract the boron as compared to beryllium. The atomic number of beryllium is higher than boron? No. As I have told you, beryllium, we can look at the periodic table for this. Let's see the periodic table over here. So we can see that beryllium is over here with atomic number 4 and boron is over here with atomic number 5. Okay, so all the options are ruled out except for beryllium has a more stable electronic configuration. So we will go for option number C. That's all about ionization energies. Hope you have enjoyed your lesson. And for further lessons and to carry it on, further past paper practice, good grades, online education, please join us at valeem.com. See you. Thank you so much.